Welcome back. I hope the tutorial yesterday was a bit helpful in clarifying some of the concepts that I had introduced in the morning. Okay. So, in any case, I'm going to give a quick recap of what we spoke about yesterday. So, we started with discussing why we need to break the manifest covariance of general relativity when we want to pose it as an initial value problem, which we can solve as a function of time or evolve as a function of time for any given system, right? And then we discussed how exactly can we do that? How exactly do we do that? Just to recap, we introduce the notion of a time direction through a scalar field whose level sets are space-like slices. They are space-like everywhere, from everywhere throughout the universe, right? And then, having introduced this foliation of space-like slices in 4D space-time, we project our 4D tensors on the slices as well as normal to the slices. And we project, through these projections, we find that there are some equations that come out when we write Einstein's equations using these projected tensors. Some equations that describe how the geometry should be within each slice, no matter what system you're solving, whether it be one black hole, two black holes, no black holes, and so on and so forth, just a fluid field throughout the universe. Those constraint equations have to be satisfied as a general geometric principle, right? And another set of partial differential equations came about which govern how the geometry evolves from one space-like slice to another as we move forward in our chosen time-like coordinate. We also discussed how to choose these coordinates and what does it mean to choose these coordinates. It could mean a specification of the lapse function or the shift vector field, lapse scalar field or a shift vector field, or it could be the specification of some equations that control these lapse and shift functions. So the second formulation we spoke about, the generalized harmonic formulation, that doesn't actually specify the lapse scalar and the shift vector field. That actually provides some evolution equations for those gauge degrees of freedom, right? And somebody asked me in the morning, before this lecture, what would be a good choice of these gauge degrees of freedom, right? So a good choice for these gauge degrees of freedom is extremely critical. It's actually a ongoing question for research. It depends entirely on the problem you are trying to solve. Typically, the rule of thumb should be that your your coordinate, these lapse and shift fields should be such that the resulting coordinates simplify your ultimate solution. For example, if I have a scalar field propagated through space, right? Now imagine if I chose my coordinates in a way that the proper distance between the coordinates also oscillated as in proportion to the actual amplitude of the scalar wave. In other words, my coordinates themselves were oscillating, similar to what the actual scalar wave that is propagating through is doing. In those coordinates, what we will have as the solution for the scalar field, it will be a constant basically. That's because you have absorbed the dynamics of the scalar wave in your coordinates themselves. So your solution becomes a lot simpler. And because you have specified the coordinates yourself, you already know the dynamics of them. So writing the solution becomes a lot more trivial. So this is a very simplified example. In practice, it's a trial and error sort of iterative procedure that helps you build better and better coordinate conditions as you go along. Especially for dynamical scenarios where you have multiple black holes in the system. For example, one problem that often occurs is the collapse of the proper volume element. So what happens in some gauges, for example, the simple harmonic gauge, where what happens is that the lapse function can collapse to nearly zero between the black holes as two black holes are about to collide with each other. Okay, so this harmonic gauge is something that people use in electromagnetism and people use in GR, especially people working on post-Newtonian theory and so on. It simplifies life quite a bit. it is equal to the generalized harmonic gauge with the source function equal to 0. It's by the way the gauge that was used by Yuan Chok-Bruha nearly 100 years ago to prove that GR has unique solutions. As you go, if you start with a given well-posed solution, then after a short amount of time you will end up with a unique solution later on. So that gauge simplifies, while it simplifies analytic calculations, it has numerical problems in dynamical spacetimes. And the problem is that the lapse function actually collapses to nearly 0. What does that mean? What that means is that now think of the proper volume element. So coordinate volume element is say d3x. Proper volume element is square root of g d3x. And square root of g is given by alpha times square root of gamma d3x. Okay? So alpha times square root of gamma is the ratio of proper volume to coordinate volume in an infinitesimal element. Right? Now if your lapse is collapsing to 0, that means in a unit coordinate volume, the amount of proper volume you can fit in is becoming smaller and smaller and smaller. So if you're doing a simulation of a fixed proper volume cube, you'll need more and more grid points. You'll need more and more coordinate volume to fill up that proper volume that you're simulating. Right? Which means you'll need a lot more grid points as you go along in the simulation if your lapse is collapsing to, square root of dead g also, for example, collapsing to 0. So the choice of these variables is important, and in fact it's almost impossible to have these choices as analytic prescriptions in general. What we typically do are prescribe evolution equations for these gauge degrees of freedom. In for example, the generalized harmonic gauge, we provided some evolution equations for these gauge degrees of freedom, right? So that's just wanted to talk about that a bit to give you an intuition as to what is the meaning, what is the goal of when we go through this recipe. Instead of going through the steps one by one, we should understand what is the importance of each step when we are trying to actually solve a problem in full nonlinear. And we talked about the initial data, right? And we talked about that how a conformal formulation where you rewrite the metric in terms of a conformal factor and a conformal metric, and you specify, I mean, this is just a choice which has been motivated by its simplicity in understanding the choice. And in this particular setup, free data is provided for some subset of the final variables, whereas Einstein's constraints are solved for another subset of variables that we have. And while solving the constraints, because these constraint equations are elliptic partial differential equations, you need boundary conditions. For example, if you solve for the motion of a drum which is stretched onto a circular ring, you need the boundary conditions for the surface of the drum at the ring, at the boundary. Similarly, you need boundary conditions for every variable that you're solving for when you're solving constraints. And it's these boundary conditions through which your physics can be made to enter the situation, the initial data basically, right? Then we talked about how to actually solve the evolution equations. We discussed there are two broad ways of evolving these evolution equations. One would be the constrained evolution, where you actually, as you are doing the evolution, you're also solving the constraint equations. That is extremely expensive. It's prohibitively expensive. That's safe to say that it is not usable in practice. In practice, however, what is used is unconstrained evolution. You start with initial data where constraints are satisfied by construction, right? And you hope that as the solution is evolved, initial data is evolved forward in time, these constraint equations remain satisfied throughout, which is, by the way, analytically guaranteed. But numerically, it is absolutely not guaranteed. Any small numerical truncation error, round off errors, will and can grow exponentially as a function of time, if not explicitly made to decay. And that was a formidable challenge that people solved by introducing additional terms in the evolution equations, which were simply sort of multiples of the constraint equations. So they did not change the physical solutions of the evolution equations, but they make the physical solutions attractors in the solution space. Any deviations from these physical solutions quickly decay away on a time scale that you can control by controlling the time scale of those coefficients in front of the constraint equations that you have added here, right? Okay, and the time scale, how do we choose this time scale? This time scale has to be chosen in a way that it's not too long or too short. If it is too short, then you're adding a new time scale into the problem. Suppose you make it too short, your time scale is of damping is smaller than any physical time scale in your problem. Then what have you done? You have asked your evolver, PD solver, to solve for a new time scale that you have introduced by hand. It will make the time steps go slower. You'll have to take smaller and smaller time steps now for solving a problem which is already expensive to solve. So that's a bad choice. And if you make it too large, then your constraints will grow to some finite level, then go down, grow to finite level, decay down, and so on. And that's not desirable either. So typically, yeah. Mhm. It should be short, not too short. It should say of the order of 10 time steps that your solution solver is anyway taking. It should not be so short that you introduce a new time scale into the problem. That's all I'm saying. It should not be too short. Suppose you make the time scale to be 10 to the power minus 10 m, and your integrator is taking step sizes of 1 m. Then what will happen? Your integrator will be forced to take 10 to the power 10 steps to do what it was doing in one step earlier, approximately speaking. So that's to be avoided, of course.
Regarding this number of the grid size, so if I have, let's say, gravitational wave signal like H-spiral, merger, and ring down part, so when I'm trying to simulate in NR, do I always go ahead with a fixed grid size, or I say that okay, H-spiral is kind of easier to handle, I will have less grid size, but towards the merger, my grid size should be over.
This is exactly sort of the answer to your question. Oh, by the way, earlier on when I said lapse collapses to zero, I meant dead G collapsing to zero, the spatial volume element collapsing to zero. That's a mistake. Now, the number of lines here at any given time is the number of grid points in a particular subdomain. The subdomain is fixed. The number of points is increasing as you go along. One more point added here, one more point added here, one more, one more, one more, one more. And this is merger, this black line. Oh, no, this is not merger. Actually, I don't know what this black line is. Let's just ignore it. And more grid points are added close. Merger is the end here. The whole graph ends at merger. So you see the number of grid points. In fact, this is the number of grid points. It,
Only small across the entire domain, or like is it
In fact, this actually, if I remember right, is showing one of the spherical shell domains around one of the two black holes. So it's one of the subdomains that is most seriously affected. So I didn't talk about, for example, this figure. Yesterday I skipped over this. But what this is showing is some sort of noise features in our initial data which are propagating outwards. So this is the source. In here are two black holes, right? And this initial data has some unphysical frozen gravitational waves in it, which are propagating outwards. And at some point, they just leave the domain. Okay? That's not the point of what I'm trying to say. What I'm trying to say is, in this figure, the Mesh refinement is trying to actually capture these high frequency erroneous features in the initial data. And you see this color here shows the number of grid points. And so as if you played a movie here, what you will see is this colored sort of ring expanding, expanding, expanding until it hits the boundary and then going back to just blue color. So yeah, actually the color bar shows the number of grid points is the color, right? So the point of adaptive mesh refinement is it tracks very well where you need the number of grid points to be more or less and so on.
That is governed by the evolution equations.
That is governed by the evolution equations indirectly. That is governed by the problem you're solving. Suppose you were solving for a Kerr black hole doing nothing, then the number of grid points will just be flat forever. But if you have a two-body problem or anything complicated, that I mean, it's governed by the problem.
So one more question. So the actual discretization that we choose for spec it's spectral, and for other it is finite difference. So what is the exact boundary condition that we apply on our equation?
Which boundary? The boundary between subdomains. So let me go back to one of the figures which showed subdomains. Good. I'm getting good questions today. Okay. So there are multiple boundaries, right? So this is the whole domain. There's a whole domains' boundary, which you can see here. This is a slice, equatorial slice. Then there will be one more boundary here at the excision surface, inside of which there is no grid point, right? And similarly for the other black hole. So there are three boundaries. So those are the three main boundaries. Now there can be subdomain boundaries. For example, each of these dark blue circles is a subdomain boundary between, for example, this domain, subdomain, and this subdomain. This and this has this as the boundary. So which boundary are you asking about?
So regarding the subdomain, I can understand you demand continuity of the solution.
Right.
But I am more concerned about the overall boundary and the boundary where you are excising the singularity.
Perfect. So let me answer the simpler question first. Okay. So this is a space-time diagram for the inner two boundaries, right? Because I'm choosing my boundary to be right inside the parent horizons. You tell me, will I need any boundary conditions? When do we need boundary conditions? If there is, correct, and if there is interaction of solution on both sides, right? And especially on the side we care about, right? That's when we need boundary conditions. So here, however, the interaction is only in one direction. Information or characteristics or whatever modes you have in your solution will propagate only into this red tube. Never it will come out of the red tube. And since I only care about the exterior of the red tube, I don't really need to provide any boundary conditions. I just don't change the boundary data at all. Now, at the external boundary, however, we have to provide boundary conditions, right? So what we provide are boundary conditions on outgoing modes, and we make sure that outgoing modes are untouched. So they are allowed to move out without being reflected or stuck, stalled at the outer boundary. And for the ingoing modes, we set their values to be exactly 0. We don't want anything to be entering from the external boundary, right? Now that's for a normal binary black hole problem. Suppose you wanted to do gravitational collapse and you wanted to inject gravitational waves and you wanted them to collapse into a black hole. Then what will you do? You'll still make sure outgoing modes are outgoing, but ingoing modes that's where you will insert your gravitational waves. In the ingoing modes at the external boundary, you will insert by hand whatever gravitational waves you want to actually enter your domain, right? And then those waves will come into the center and collapse into a black hole eventually and so on.
Just a quick follow-up.
Yeah.
So how do we actually implement it using the code? In the code, I mean, do we use like those points or one-sided derivatives that are finite difference? Or I don't know how it's done.
You can do one-sided derivatives. In spectral methods, you don't need any special treatment because in any domain, you can calculate derivatives anywhere. So the boundary is no special in that sense. So you, for example, if you wanted to put boundary conditions on the derivatives of characteristic fields, so on the outer boundary, you set your characteristic fields time derivatives to be equal to my boundary values. Now you transform these derivatives to the derivatives of the evolved variables. You go from characteristic variables to evolved variables after specifying the characteristic variables.
So here I am a bit confused because the actual evolution is occurring on space-like hypersurfaces, right? So, so why are we then imposing boundary conditions on characteristic hypersurfaces?
No, not characteristic hypersurfaces. No. On the characteristic modes. You can, so if you have, you can specify your, for example, whatever variables you're solving for, space-time metric pi and phi IAB, but the actual characteristic mode, sort of the eigen modes of the system, will usually be some combination of these. The actual independently propagating modes will usually be some combination of these. You can go from metric pi phi to some other combination of evolved variables. You can evolve metric plus pi, metric minus pi, and phi. It doesn't matter. It will not change the characteristic or the propagating eigenmodes of the system. So you set boundary conditions on those, and then you transform back to whatever variables you were actually evolving, whichever, for whatever reason you might be choosing those. Good. Okay. Yes. Now, we already spoke about why we need to increase and decrease the grid resolution as a function of time, right? Because of the dynamics of the problem. And we talked about, So one question I get also quite commonly is that how does it change? How does this entire treatment differ between, say, non-spinning black holes and spinning black hole binaries? If you notice, none of the discussion we had so far depended on the details of the apparent horizons, or details of the black holes. We don't actually put in the black hole by hand. The black hole apparent horizon has to be discovered from the metric data. What we have at t equal to 0 is full metric tensor everywhere on the slice. And what we are evolving is the same full metric tensor everywhere on the slice, right? So the horizons have to be discovered in your metric data. That's why we need to not find, we don't need to solve for, we don't need to put in the parent horizons by hand. We just need to solve for them. That's why we need to track all of them, track them at every time step and so on. Okay. Good. So thank you for these questions. Then let's move on. So let's look at some of the results that have made the highlights over the years. At at the very beginning, this slide shows one of the earliest waveforms that were calculated using the spectral Einstein code. And 2007, this corresponded to an equal mass system, two black holes, which are not spinning at the beginning, and they in spiral for about 15 orbits before they merge. Now, these are Einstein constraints over here. These show the norm of those constraints, right? And at every time, what is done is we take the L2 norm of the constraints at all grid points, for all grid points, right? So this is what the top and the bottom are showing. And different lines here correspond to a different level of spectral resolution. Okay. So as you see, and as is expected, the power of spectral methods is shown very clearly here. As you increase the number of grid points in a linear fashion, your errors decrease in an exponential fashion. These are your Einstein constraints. These are basically your errors. They should be identically zero. And they are decaying on a log scale almost uniformly. That means they are going down exponentially as you increase the grid size. Right? There are some transients here at the beginning which quickly leave the domain and never enter. How do I know? Because this peak lasts almost as long as the size of the domain on the x-axis. So if the size of the domain was 700 geometrized units, beyond 700, the noise pulse has left the domain. And if it had come back, it would have been visible here. Or if there had been reflections from the outer boundary, they would have been visible here. Right? And trust me, there were many, I mean, before getting to this figure, there were many cases where there would be reflections and so on, and you have to make sure your boundary conditions are better and so on. So this is just the final product. You do see reflections often.
So after this jump, will be the waveform is reliable, is it?
Yes.
So this is what is referred to jump radiation.
This is the pulse of jump radiation.
But
Yes.
why does it increase again?
This is merger. This is at merger. So everything just becomes more nonlinear close to merger. And this whole figure can be shifted down in the y-axis by just say doubling the number of points. So it's all about now money, how many computers you have. The more computers you give me, the more I can bring the whole curve down. But I cannot change the entire shape of the curve. That depends on the problem. Right? So for example, if you had hyperelliptic orbits, suppose you had highly elliptic orbits, what you would see is periodicity in this increase, right? At the moment of closest passage, the errors would increase up and then go down, up, down, up, down, up, down, and so on. This is only for a quasi-circular in spiral, where the in spiral is monotonic.
Another question.
Yes.
So, why do you say like it doesn't matter whether the black hole has spins or not? Because I expect when we talk about spinning black holes, we have another extra degree of freedom and
We don't. Why? Why do we have an extra degree of freedom when we have spinning black holes? We're solving Einstein's equations. The equations don't know if there's a black hole at all. They will have the same number of degrees of freedom as they've always had. Right? I think what will change is spinning black holes will introduce another time scale into the problem. So your integrator will be slower. It will induce oscillations in the horizon. So another length scale will be introduced. So you will need finer grids near the horizons. But I emphasize the treatment of Einstein's equations is agnostic to the problem, is what I'm trying to say. I would take back my words when I said it doesn't matter. It does matter. The problem becomes more expensive.
metric changes right when you include spins.
Yes, the problem changes. Resolving the metric needs more grid points, smaller time steps. But beyond that, the formulation is untouched.
But see, I am like trying to simulate formation of a short sheet black hole, and then I later say I want to simulate a curved black hole. So where will I exactly change? Because we start with the same set of Einstein's equations. So will we do something with the initial data, or is it the answers we are taking?
Only initial data. Only initial data. Only. Right? As we discussed, it's through, in fact, specifically the boundary conditions when you're specifying your initial data where you insert all the physics in your problem. Okay, good. Excellent. So this figure here shows the accuracy in terms of the final waveform. So how do we measure it? We take waveforms at successive resolution 1, 2, 2, 3, 3, 4, and so on, and we take differences between the solutions at successive resolutions. And wait a second. Yes, this shows the difference between successive resolutions. Right, and you can see the difference being the smallest for the highest resolutions. And again, the differences are decreasing almost exponentially along the y-axis uniformly. Right. So this is the power of spectral methods. Spectral methods are quite complicated and messy to implement, but once you implement them with a small number of grid points, you get away with a lot. You get to solve complicated problems much more cheaply, with much fewer grid points, much smaller amount of computing, and so on and so forth. Put another way, for the same amount of computing, you get to run your simulations for longer and have more accurate simulations. Okay, so the first open access catalog of simulations, which had around 174 simulations, was released in 2013, so around 12 years ago. And this, I believe, are all the waveforms that were part of this catalog. Right? I think blue and orange are the plus and cross polarizations that were extracted from them. You can see some simulations are longer, some are much shorter, and so on. Typically, shorter ones are older, longer ones are more recent, and so on. So let's look at a full 3D rendering of the simulation output, right? So I'm sure you have seen this video before. Uh, what is shown here in the outer region is the outward propagating gravitational wave front. Okay, and in this inner disk nearby, what the color shows the spatial, the height shows the spatial curvature, and I think the color shows the time dilation. Sorry, it's an old movie. I'm missing on the details. Yeah, the height shows the 3 Ricci scalar. Yes, and the arrow shows the flow direction of flow of time. And this is the orbital plane of the system. So the two horizons here, they initially had misaligned angular momentum, which means the orbital plane of the system will itself precess. So the camera is fixed, it's the plane that is changing orientation here. And the initial data here corresponds exactly, well, almost exactly to the source binary for 150914.
Sorry, what was the height you said?
Height is the 3 Ricci scalar. And that's the moment of merger. You see, a common horizon forms outside enveloping the two inner horizons. Okay, and then it very quickly settles into a Kerr black hole state. And you can see the brightest wavefront here corresponding to the moment of merger. Right? So 3 years later, another set of 100 waveforms were released. That used to be a big number in 2016, 100 waveforms and so on. Now 1000 is a big number. So things are getting better.
I have a question.
Yes.
So one thing, when you see gravitational waves, you are tracking the evolution of Scheibe, right? And the second question is that when you run the simulation, like how long do you run it? Like, do you capture properties of the late-time wave into the simulation?
That's if you want to, you can capture the late time properties of the horizon dynamics.
Yes, unless the Q&A bringing dies out, if you want like to capture how the late time will actually evolve. You know, but the perturbation theory how it does.
Mm-hmm.
But I don't know if we have extra stuff coming in from the simulations. It does it follow Price's law?
So, for example, I think Sumanto is not here, but Sumanto will talk about nonlinear, may talk about nonlinear ring down modes and so on. And those have been found in the ring down waveforms coming from numerical simulations. Basically, all nonlinear features you would expect to come out of Einstein's equations are present in the solution. You have to find a way to extract them. Having said that, you also need to have high enough resolution post merger to be able to resolve the features you are interested about. For example, if you're interested in the nonlinear ring down modes, quasi normal modes, you'll have to resolve possibly the horizons possibly better than we resolve them by defaults. But that's not difficult. You can set the resolution requirement to be much higher than we have currently, and then you will be able to. Okay. So 2018, so 13, 16, 18, another set of simulations. This time, a major push was done to release nearly 1,000 simulations into the uh, public domain. And what is more interesting than the number of simulations is that they were longer than most of the simulations in the past. Right? Some of the simulations were actually quite long, more than 100 orbits long. So that actually is something that is very difficult to achieve with finite difference codes. The requirement for long-term stability are very stringent. Why? There are many problems that affect long-term stability, and everything boils down effectively to the resolution that you need. If you want your simulations to be stable for a longer and longer time, you need more and more resolution to resolve smaller and smaller features that might introduce errors into your simulation. So with spectral methods, you can do that cheaply, right? Okay. So that's what I was talking about, stability. And because of AMR and better control systems, we can now easily perform simulations that are these long. In fact, for example, this one is about yes, 100,000 m long, mass ratio 7, 180 orbits. Last year, we did a few fully precessing eccentric simulations that were nearly as long as this. They were actually 60 to 80,000 m long. And we did not have to do anything special to run those simulations except for specifying the initial data accordingly. Right? Okay. And the bottom figures here show how accurately we track the orbital phase, again at different resolutions. So these integers are resolutions. 0 is the lowest and 3 is the highest here, or 4 is the highest here. So it's 1 minus 0, 2 minus 1, and so on and so forth. Okay, how expensive are these simulations? Well, how accurate are these? There's a measure of accuracy called mismatch. It's an overall, it's a measure of accuracy in an integrated sense. You take your waveform, whole waveform, you can compare it with the true waveform and integrate the differences. And that approximately is what mismatch is. Okay. Now, computational cost is given here depending on the length of your simulation. For a fiducial 20 orbit simulation, the cost is around 20,000 CPU hours. This has now come down by a factor of approximately 2. With the same length now costs about 10,000 CPU hours, which means we can run longer simulations more easily. And this is showing the number of grid points that you asked about. Again, at different resolutions, you can see the grid points as a function of time, and all of them spike close to merger. Okay, so let's talk about some of the applications of numerical relativity that we have in since the last decade and a half that we have been able to do these simulations. So there are conventional applications where NR is applied to develop waveform models. There are also more progressive applications where NR can be used directly as waveform templates, which in turn are used to classify signals as signals and not noise, then characterize those signals and so on. So conventional applications include calibration of waveform models, and pretty much most of the waveform models that capture the inspiral and merger ring down process are calibrated to modern numerical relativity simulations. A lot of them are calibrated to spec simulations. So for example, I mean, this basically ranges from non-spinning quasi-circular to aligned spinning quasi-circular to spin precessing quasi-spherical and aligned spin or non-spinning eccentric orbits and so on and so forth. All the waveform models that have been used to analyze LIGO-Virgo signals were calibrated to a few spectrons at least, right? But going forward, this is not, I may be giving the impression that we are done now, we can solve this problem and we can move on and retire. That's not certainly at all the case. In fact, this figure here is from a paper by Michael Purer and Carl Haster, which shows the accuracy requirements for these waveform models as a function of detector sensitivity, going from least sensitive to most sensitive from left to right, for a mass ratio of nearly 1 in the left panel and a mass ratio of 3 in the right panel here, right? And there's a lot of things in this figure. The important thing to note are the pink bands. And is approximately the accuracy of current waveform models that we have. The green band here is approximately the accuracy of current NR simulations, right? Not all simulations are equal in accuracy. Some are less accurate, some are more accurate. And the brown band here shows the fundamental detector data calibration errors. So fundamentally, how well do we know the data itself coming out of the instruments? So any accuracy below the brown level is not useful, because you'll be then dominated by genuine ambiguities in knowing the detector's characteristics. But
Band is the span between NR waveforms.
yes,
Keep fixing the parameters same.
yes, at different resolutions, for example, right? So for two equal mass systems, now sort of accurate enough, necessarily. And by the way, how do we know what is accurate enough? These diagonal lines are what are telling us what is accurate enough. So diagonal lines actually are the requirement of accuracy for each of these instruments, right? So O1 is LIGO, Virgo, first observing run. HLVK will be the design for detector network. Then we have the A plus detector configuration, Voyager configuration, Einstein telescope, and then the combination of Einstein telescope and Cosmic Explorer, right? And naturally, as the instruments get better, our requirements become more strict on a log scale, right? So models are certainly far from being accurate enough. And even NR is far from being accurate enough, except for close to equal mass systems, right? So there's a long way to go. Okay. So how can we get there? A small snippet, we can get there by, for example, first step would be to bring the red and the green bands together. Let the waveform models become at least as accurate as the NR information currently. And currently, what these models do is they don't calibrate the internal details. They only calibrate the final output of the model, which is the waveform against NR data. If they were able to calibrate, for example, the orbital dynamics inside the model, whatever gauge they might be using internally, to numerical relativity in the same gauge, of course, then we would be able to have a better handle on the overall model and so on. So this is possible. How we figured out a way to do this, the way you can do this is alongside evolving Einstein's equations, you pick your model, you pick its gauge condition. Typically, that's a differential equation. You also solve that differential equation alongside evolving Einstein's equations, which means now you can write the coordinates that are used in your model as fields in the NR coordinates, and then you can construct the orbital dynamics in your model's coordinates, and then you can make a comparison between what is the dependent dynamics, orbital dynamics from NR versus whatever your model is predicting. So, for example, the blue here shows the in spiral of not equal mass, 1.2 mass ratio non-spinning binary, and you can see there is a jump in this radial separation. That's not because the binary is going away. That's because the definition of the radial coordinate has changed during the NR simulation. Here, this bump over here, then it goes down and collapses to merger. This is in pure spec coordinates, the generalized harmonic coordinates that we are using. And the black dashed line, which is difficult to see, is the equivalent in spiral in the harmonic coordinates that PN uses, right? And by solving the harmonic gauge equation, we are able to get the red curve here, which gives us the trajectory of the actual NR simulation whatever the black holes were doing in the PN coordinates. So anyway, this kind of comparison would enable better modeling by pinning down intermediate stages in waveform models, for example, right? You are free to solve all sorts of equations alongside Einstein's equations to study these things.
One question is that previous to previous slide. So this one, I mean, kind of very stupid, but if I have continuous, let's say, some future hypothetical detectors with increase and increase sensitivity, then the number of template requirements will be more and more.
Yes.
Like you have to be just an order of estimate, like if I am using Einstein telescope to Einstein and cosmic telescope together, what are the order of template change?
I don't know.
But it would be there. Right?
It would be a significant increase. Even between O1 and HLVK, there's a significant increase. I think factor of 4 or 5 in the number of templates required. That's because you are able to distinguish between, say, with less sensitive instrument, you can distinguish between a 1.4, 1.4 system and 1.6, 1.6 system, but not 1.5, 1.5 system. With an improved detector, you'll be able to distinguish between 1.4 and 1.5. With a better instrument, 1.4 and 1.41 may be distinguishable, so on and so forth. So then you need templates for every, so, you know, delta, theta, where theta is your parameters. Okay, let me skip that. And yeah, NR is used to sort of test GR by looking for consistency between the post-inspiral and pre-inspiral. So the way it is done is you figure out the final black hole's properties using only the inspiral or only the post-inspiral. And how do you deduce this post-merger black hole properties from the inspiral part? You deduce the individual black hole pre-merger, the two black holes' properties, and then you use a map to map those two numbers, or 8 numbers being the two masses and 3 spin components for each of them, to the post-merger black hole. And that mapping comes from numerical relativity catalogs. Okay.
But this assumes that described by GR, right?
Yes. So this is a null test, in the sense that a violation of this would be interesting.
And so we keep hearing this that to test GR we need to, or deviations from GR, we need to detect at least one of the overt domains and duration. Okay, so how does that fit into the test of GR? Why is the overt?
So in the ring down regime, specifically in the linear ring down regime, there are specific discrete frequencies that are the correspond to the eigenmodes of the perturbed Kerr black hole. And if we are able to measure precisely the frequencies in the post-merger signal, the discrete frequency in the post-merger signals, then we can compare them with the predictions of linear perturbation theory in GR. If they agree, good. If they don't agree, then we have a potential violation. Right? So you need to measure at least 2 in that sense, because first one will be fixed by the overall mass of the system. With just one frequency, you could have changed the mass a little bit and made it agree with whatever the GR prediction is. I mean, it will always agree with some GR prediction for some mass of the final black hole. The real test comes with the second one, fixing the first mode if your second mode doesn't correspond to what GR predicts. Okay, this I think I'll just skip. Let's move on to what do we need for scaling? What do we need to go from here, move on from here? So we discussed some of the challenges that numerical relativity faces, at least for describing the binary black hole problem or dynamical black holes in general. We discussed the problem of length scales, coordinate choice, how to put the singularities on numerical grids, how to tame Einstein constraint violations, how to resolve shocks which don't happen in black hole spacetimes but will happen in neutron star black hole or neutron star evolutions. Then the computation challenges and the access requirement. So the ones have crossed out and or faded out are the challenges that have almost been very nicely addressed already in literature. Okay, what remain are the ones that have not faded out. So for example, how to handle multiple time scales. This is a snapshot of your domain, right? So the time scales, all the interesting time scales are happening in here, and in every and basically all of the exterior volume, the time scales basically correspond to gravitational waves this time scale, right? So not much is going on in the empty space beyond the source. So why is the integrators forced to take very small time steps everywhere? That leads to a wastage of computing. and so on. So if we were able to integrate over time, forward in time, in a different, at a different rate at different parts in my slice, that would be excellent, which is the thing that I'm going to talk about later. Okay, and all of these things tie back to computational challenges. I mean, given infinite computing resources, all of this is trivial. All problems are solved. We just throw a billion points and you're done. Just go home. But we don't have infinite computing resources. So 6 is the root of everything else, right? Okay. So just boiling down those unresolved, this thing, uh, this actually brings us to realize that these are fundamental limitations of the current paradigms that are used in current numerical codes. No amount of improvement of current codes, unless their paradigms are changed, will actually solve all of these problems very well. So the new paradigms that we need are three, and these, at least at that we think are need, are these three. First one is the choice of a better discretization scheme. So finite difference is excellent for shocks and discontinuities, but very expensive. It doesn't converge very well. Spectral discretization is very good for smooth solutions, but neutron stars are going to give rise to shocks and so on. So spectral methods are not used for those. A good discretization scheme is going to be something. So this is a wish list of its properties. Okay. So it has to be local at high order. What does that mean? What does that sentence mean? It means if you want to calculate, say, spatial derivatives, second order accurate, third order accurate, fourth order accurate, eighth order accurate, the increase in communication as a function of the order of your derivatives should not be steep. Typically in finite difference, what happens if you want a second order accurate derivative? If I'm one grid point, I take information from two neighbors on both sides and I construct a polynomial and I calculate the derivative here, right? Third order accurate, 3 grid points on both sides. Fourth order accurate, 4 grid points on both sides. Eighth order accurate, 8 grid points on both sides. So you see how the communication requirement is scaling up. The more accuracy I require, the more information needs to be brought to me, to the current grid point. That we want to avoid, because communication is very expensive on modern computers, right? And then handling discontinuities, it should be naturally be able to handle discontinuities, and it should naturally be able to adapt to inhomogeneous grids. What does it mean? For example, this snapshot is showing a moment in time of a neutron star that has been disrupted as it was falling into a black hole. And look at this long tail that is spiraling into the black hole, right? So we want to be able to put grids that are dense only in this spiral and that are less dense away from it. That's what I mean by inhomogeneous grids, right? So the method should not have to do anything funny or fancy to homogeneous grids versus uniform simple cube grids and so on. So this is a wish list. Now parallelization scheme, uh, it should be able to distribute your calculations on supercomputers in a way that you effectively use all the computers currently. You'll be shocked at how much we waste computing during these simulations. I'll talk about that. And also local time stepping. I've already talked about that, being able to take time steps depending on the local needs of your problem. Okay, so this brings us back to the new code that we have been developing, which has matured quite a lot in the last few years, called Spectre. So start with what are the let's try to understand what are the fundamental limitations of modern computers, right? So on a single computing node, uh, the speed of your processors, the performance of your processors is not increasing as quickly as we thought. I mean, when I was a kid, we had a 1.4 gigahertz processor. Now we have 4 gigahertz. That's like a small step up in the speed of individual computers. And as the size of transistors hit quantum limits, that is not the way forward in modern computers anyway, other than of course quantum computing, which is probably far away. Now we have a network of computers available to us which are connected to each other by very fast communication wires. Communication sort of takes up as much cost as the computers themselves. In a typical high performance computing cluster, 50% of the cost is just the wires and 50% of the cost is the actual processors. So that's how expensive communication is, right? Okay. So the less we require communication, the better, for example. And the more we can spread out our calculations, the better. That's the two simple takeaways from this. Okay. So I've already talked about some of this. What are the fundamental limitations? I spoke about spectral methods limitations. I spoke about finite difference methods. Higher order methods require larger samples, meaning long and converge as the number of grid points. Use of MPI to parallelize your calculations. So, okay. So, there's a, let's say one has a physical domain, which one has split into n subdomains, right? And one has available to us, say, p processors. Now, the computational cost will scale as the physical volume per processor, the amount of proper volume or physical volume that you have assigned to each processor. So that will scale as order n over p. And the communication cost will scale as the surface area between each volume element and the next one. So that will scale as n over p to the power 2 by 3. So the byte per flop, the amount of data you need to move from here to there per single floating point operation, that's the number you want to be as small as possible. That will depend on p over n cube root and so on, right? So it depends on the number of processors, the amount of communication you have actually depends on the number of processors. It also depends on the number of subdomains you have divided this into. Now, typically, that's actually not only fundamental limitation. Another limitation which I have not given here is the heterogeneous nature of your problem. Heterogeneous nature matlab, a lot is happening near the black holes and nothing is happening away from it. So a lot of computing is required in a small amount of the physical domain, small region of physical domain, and very less computing is required far away from it. So if you use the MPI sort of the data driven parallelization scheme, where what you do is divide up chunks of volume and give each chunk of volume to a different computer, then what you will end up doing is all the computers that are responsible for the volumes near the black holes will keep working, while the computers that are responsible for the volume away from the black holes will be done and they'll just wait for the other people to finish. And you'll end up wasting a lot of sort of compute cycles if you divide your calculation in a data driven way. Data driven way meaning by how your data in the domain is this thing. So there are modern ways of parallelizing calculations which are not data driven. So we have to not think like physicists at all. We have to think like computer scientists here. Okay, thinking like physicists is what got us here. Only so far. I mean, from here onwards, we don't want that. Okay, so Spectre is a general purpose multi-physics solver framework, which actually is able to take care of all three of these goals, that paradigms that we wanted to switch out for modern paradigms. Spectral methods and finite difference methods, they have been by what are called discontinuous Galerkin methods, and we'll talk about some of these details later. Local time stepping is implemented, as well as a new way of parallelizing called task-based and not data-based, but task-based parallelism has been implemented. Okay, so let's talk about the discretization scheme. So when you have a PDE solvers, when you're trying to solve a system of partial differential equations which are hyperbolic, which means you're evolving them forward as a function of some time coordinate. You start with first discretizing space or discretizing time. And when you discretize time, you can use the method of lines to do the integration, and you have well-established adaptive integrators that figure out how large time steps you need to take. I'm assuming you all have taken some courses in numerical methods because I'm seeing a few people sleeping here. So hopefully this is all too simple for them and not too boring for them. Okay. So this branch is well taken care of. I mean, the standard adaptive integrators, and this is actually a simpler thing to consider, which I won't go into the details of. What I want to talk about is how to discretize space. So how do different discretization schemes differ from one another? They differ precisely in the sense in which your discretization errors are defined. Are the errors defined at every grid point? That's the pointwise, that would be the pointwise discretization, which would be the what finite differencing does. Okay. Now, or the errors could be defined, so the whole domain can be divided into small cells. And the errors could be defined in an integrated sense over each of these cells, or in an average sense over each of these cells. Okay, what's the difference between 2 and 3? You can define how you define you can choose how you define this integral. You can define this integral to be in a way that it is orthogonal to a particular choice of basis functions. So all your errors will be orthogonal to a particular choice of, say, basis function. So if you're using a particular set of basis functions to resolve your physical fields, all your errors will be by construction orthogonal to your physical fields. Okay. So depending on these three ways of defining your discretization or sense of discretization, pointwise is finite difference or spectral co-location methods. They all fall under this way of discretizing space. Volume integral would be the Galerkin's family of methods. So there are continuous Galerkin methods and discontinuous Galerkin methods. And volume average discretization would be the usual finite volume, finite element methods, which are used in fluid dynamic simulations, which are used to make the airplanes you fly in, which you probably sat here to reach this place and so on. All of those codes that simulate the dynamics of airplanes, they pretty much use finite volume methods because those are more homogeneous problems. Okay. So this is the branch that we have taken in the Spectre code. So what is the DG method, right? So this is my one-dimensional domain. I have only 3 cells in it. Very simple world this slide is living in. The green curve is my true solution, and it is expanded in each cell independent of every other cell. Okay, and the blue is my best representation of the solution in that cell. So for example, this blue would correspond to a constant plus a linear term. So only 2 coefficients are there. A constant which sets the overall height of the blue line and the slope of the line. Same thing here, independent of each other, right? The discontinuous part in DG methods is that the cell boundaries, treatment of cell boundaries is such that continuity is not a requirement in this. What you need is just, suppose you think of the kth cell, dk. What you need is information to flow from the neighbor to this cell and from this neighbor to this cell. And you can prescribe approximate numerical fluxes that are given in terms of the fields in this cell. The fluxes will be how much of the propagating modes are entering in from this direction and how much of the propagating modes are entering from this direction. Okay. So notice the key thing that we have solved by doing this. Actually, many key things we have solved by doing this. First, you want a second order, third order, fourth order, fifth order, nth order accurate derivative that only depends on the number of basis functions chosen in this small cell. It doesn't depend on its neighbors. I can choose 20 basis functions here and 5 here, right? So I can define my derivatives of that corresponding accuracy here and less accuracy here. There's nothing stopping me from doing that. It doesn't require dk to become bigger. So communication is not required for higher order accuracy. So it's local at low order accuracy, local at high order accuracy. It can handle discontinuities as long as discontinuities happen at the boundaries of these cells. Or in other words, as soon as we see discontinuity forming, we refine our grid and we make sure that cell boundaries align with the boundary of shocks, for example. Right? A simple example would be imagine simulating a spherical planet or star with a crust, right? So your cell boundaries will be at the crust and new cells will begin in the exterior of the crust and new different cells will be at the interior of the crust. As long as the crust is at the boundary of some cell interfaces, we are good. Okay? And in homogeneous grids, I mean, there's nothing special to be done. The cells can be arbitrarily small or big. So you can put a lot of small cubes together or a lot of large cubes together and so on. Okay, so here's a comparison of DG methods to finite difference spectral methods and finite volume methods. Okay, red is bad. So this spectral methods fail at neutron star simulations, finite volume methods fail at higher order accuracy, and finite difference methods also are similar to finite volume methods. Okay, any questions so far? Yes.
So DG also uses the information cell
But only from one neighbor. Only from one neighbor, not from, if I require 8th order accuracy, I don't need 8 neighbors here and 8 neighbors there. Just one neighbor.
I mean, okay, so one neighbor right
I mean, right, left, top, bottom, front, back, depending on the dimensions of your problem. This is a one dimension, so one neighbor on each side. Okay, so I'm going to pause here for 5 seconds and see if anybody is awake. It's yellow means it's not ideal. It can be used, but it becomes very quickly very expensive to use it.
just like apart from these, are these the only methods or are people do they try to use like something called optimization methods or they fail?
Optimization methods for discretization. Maybe I'm not understanding what you want to ask.
Because how I was thinking that if I have a function which is multi-valued and it is very difficult to find its let's say maximum or minimum by if it is not analytic, I have to find a minimum. So I can either do MCMC to find the number and so on and so forth. But there are these optimization methods also which try to find that kind of thing. So in parallel to that, I was thinking that if you have some optimization methods, but I think they would be too costly. They suffice like these methods.
So optimization methods are solving a different problem. In fact, they don't even necessarily discretize your space. They don't.
Yeah.
You can take, if you have to optimize a scalar function in 3 dimensions, you can step in the 3 dimensions in a continuous fashion. You don't have to take steps on particular grid points. So that would be a different kind of problem, right? Okay. Okay, so in practice, however, one place where DG methods not do very well in practice is in handling, in making sure that the shocks, well, one place where we fail is making sure that all the shock formation or discontinuities align perfectly with the element boundaries. That alignment has not been very easy in practice in curved spacetime. So what Spectre has now is something called a combination of DG and finite difference methods. So what this does is, if you have your entire simulation domain, you're split into small cells. Each cell may you're using DG method to integrate to discretize your fields. Now, if in particular cells you know a shock is forming or there's an indication of a shock is forming or discontinuity is about to form. For example, two stars are about to collide. Their crust, the moment they touch, will form discontinuities, for example, in density and so on. right? So whatever cells are in about to experience shock formation, in those cells we get rid of dg and we resort back to finite differencing only. And as soon as the shock has moved out of those cells, the shock front has moved out of those cells, we go back to doing dg methods again. As soon as the solutions are smooth again, we go back to doing dg methods again. Okay, so this is the typical flow chart of how a time step is now done. So you keep doing, time, you keep integrating time using dg scheme. And if you don't find anything fishy with it, you just stay in this loop. However, if you find that your solution is not, smoothly related to the solution at the previous time step and so on, you then go to doing a time step using finite differencing. And if one step works with finite differencing, then you go back to the dg loop. If not, you stay in the finite difference loop as long as you need to, unless you are able to get out of that loop and you go back to doing dg. Okay, so local time stepping, many times before, I hope you'll remember it. Most of the domains are empty. Most of the domain is empty. All the fun is happening in this tiny region inside. Everything else is basically vacuum, right? So what you want is to be able to evolve time depending on where you are in the domain. If we collapse this 3D domain to just this one line here, then this is my outer region. This is the proximity of smaller black hole. This is the proximity of bigger black hole. The smallest length scales will be in the proximity of the smaller black hole, obviously. So the smallest time steps you need to take is in this cell, and then you can take larger time steps, slightly larger in this cell, and much larger time steps in cells that are away from the problem at all. So this is what is called local time stepping and so on and so forth. Okay, this has been implemented, and I think now we can stably achieve a ratio of 16:1 in terms of the largest to smallest time steps that we can take just out of the box. Better than that, you'll have to tune the code to your problem at hand, but 16:1 is not bad. That means easily a factor of 16 reduction in the cost of evolving in this entire region of empty vacuum. Okay, I talked.
As the mass ratio increases, this time stepping needs to be incorporated.
Yes, absolutely, absolutely.
Like for EMBs,
Even for if we are able to do IMRIs, IMRIs. So EMRIs are extreme mass ratios, meaning 10 to the power 5 is to 1, 10 to the power 6 is to 1. We cannot evolve those systems, right? We can best, at the moment, we can evolve say 10 is to 2 is to 1 systems. And yes, in general, with mass ratio, you will need smaller time steps here. So this ratio will have to increase. Okay, I already spoke about the parallelization framework. So you have data based. Actually, this is a misnomer. It's not an MPI domain based. It's a data based parallelization where each subdomain is assigned to different processor, right? And the slowest processor makes everybody else wait, right? So we don't want to do that. We now use what is called task-based parallelism. So you divide your computation by tasks and not by physical domain. What does it mean? So suppose, let's focus, this is your computational domain. Instead of 1D, I'm taking 2D now, right? Let's focus on just this cell. This has in 2D 4 neighbors, one up, down, left, right. And the purple is a fictional entity which is the boundary between these two cells. This is the boundary between these two cells. So purple block denotes the calculations you need to do at the boundary. The blue cyan blocks denote the calculations you need to do in the cell. Okay. So if you want to evolve Einstein's equations in this cell, you'll typically need to do calculations here as well as get information from the purple rectangles here, which in turn are getting their information from these. So you have a sort of a dependency graph of your calculations. In order to calculate the right hand side of say the first Einstein's equation, I'll need the following data in this volumes. In order to calculate second and third, I'll again need only data from the volume, but then I'll have to set boundary conditions for which I will depend on the boundary data, and this boundary data in turn will depend on the volume data in the neighbor. So you can write all these calculations as a graph, right, as a dependency graph, where some calculation will feed into another calculation, this will feed into two more calculations and so on. So for example, this particular term that needs to be calculated depends on these two and it feeds into the next two and so on. So you build this graph first, and there are very easy ways of building this graph. Career computer scientists at UIUC have developed a very nice library to do the building of this graph for you, and doing the next step, which is parallelizing this graph. What does that mean? So now each of these circles are computations, so they are tasks, but even the arrows can be made to be tasks. Arrows are flow of data from here to there. Even the communication have been made tasks. So you have this tasks and these are all tasks. You put all the tasks into a global queue, and these are your cores, right? So this global queue will just keep pushing tasks to cores as the cores become empty and available and so on and so forth. What does it mean? That it means that suppose this is currently being the task being in, being done right now, right? As soon as this task is done, suppose the neighbor has not yet finished. The planning will be such that the computer which will solve the will start moving the data. It will already plan for the next task in future. Okay. So what happens is the communication cost gets hidden behind the calculation cost. Some calculations are being done, or in the back communication is already happening from the calculations that have finished to the next calculations that have to happen. Okay. So everything becomes a task, and you typically pay a small price. So if you have each node in your cluster has 24 cores, you sacrifice one core which is responsible for the communication tasks alone. So that sacrifice will make sure that your data is flowing even before the next task has begun. All the prerequisites are already there. Okay. So by sacrificing that fixed amount of computing, you basically get no latency because of communication. Okay. So some results. This is actually quite fresh from last year. This is the first binary black hole simulation that we have with Spectre. The colors are arrows are identical to the movie that we showed. These are the two horizons. And this is the waveform coming out of the simulation with Spectre. These are the horizon trajectories. I mean, no prizes for guessing. This is an equal mass system because of how symmetric the trajectory is. And this is the domain or the grid that we used here. So these are the individual horizons. This is the common horizon, but the horizon has nothing to do with the underlying domain structure. You see, these are rectangular domains that are getting slowly deformed into more circular shapes as you get closer to the singularity. This is just a new choice of domain structure that Spectre uses and so on. Okay, and just to show that these solutions are actually physical, this is again the norm of constraints as a function of evolution time. This is some initial error pulse, junk radiation, and then it remains pretty stable at 10 to the power minus 7 until merger, at which point it grows and we are trying to figure out why, and it has to be fixed. This shows the properties of the common horizon that forms at merger as a function of time. So the first time it forms at is around 4900 m, which is right here, and mass, Christodoulou mass and areal mass are shown here. Sorry, spin and areal mass are shown here, and comparison between Spectre and Spec looks pretty good, right? So we can do simulations of binary neutron stars. So this video here will show us, unmagnetized neutron stars being simulated by Spectre. Okay, so the colors literally show the density profile in the equatorial plane. There's nothing very fancy going on here. The star merges and that's about it. There's no magnetic fields or anything. There's the two stars are equal to each other. They have the same equation of state. So it's a fairly straightforward simulation that was possible more than 10 years from today. But what is interesting is that finally we can make it happen with Spectre, and things should scale much better with Spectre. Okay, speaking of scaling, this figure, in fact, now I realize I should have put much earlier in the talk to show you the power of these three new paradigms, right? So this green curve is current generation analysis and how well for solving some problems, how well will your solution time change as you throw more and more cores at it. As you put bigger and bigger computers at work, does your solution get, I mean, you get the solution faster and faster. That is true for some time around 100, 200 cores on, sorry, 20, 30, maybe around 70 cores it saturates. At 100 cores, it has definitely saturated. Beyond that many cores, the improvement in performance is very slow, even if you throw more cores or more money at it. Can we solve it with more money? No, we can't. So we literally need infinite computing power if we stay stuck with spec and the first generation NR cores. Spectre, on the other hand, we were able to test for not the BBH problem, but for simpler problems. We were able to test the scaling up to 500,000 cores, right, on national supercomputing facility in the US, and it scales almost linearly. And what's the great part here is that we didn't have to do anything special to get this curve. Just install the code, set up initial conditions for the problem, and let it evolve. And that's it. We didn't have to tune it to get such good performance out of, good scaling out of it. No, it's just built in into the numerical methods that are underlying. So Spectre you can use for numerical relativity, but you can also use for evolving fluid mechanics problems with friction, without friction. You can play around with scalar waves in curved space time, and so on and so forth. With Spectre, I mean, it has a lot of things that have been implemented in it, which brings me to this final slide, where I thought I'll just walk you through the documentation of Spectre, and we'll end at that. Oh yes, Spectre is open source. Did I not say that? It's open source. It's open to everyone for use. You can install it on your laptop and you can try it out today. Okay. So this is the documentation page for Spectre. Right? And there are some, nice figures that have been produced by Spectre that have shown in this talk, but they're also collected here. We can generate binary black hole data with Spectre quite easily with out of the box, and you can use this initial data in any code if you want to use it with spec, which is not open source. But if you want to use Einstein toolkit, which is open source, you can just take this data and use it. Now, how do you install it? Right? So installing it can be quite a challenge, which is why I will strongly recommend you use something called a Docker, something called a container, a software container. And popular containers are Docker, Apptainer, Singularity, and so on. So what are containers? Containers are modern software engineering concepts which make sure you are insulated to the changes in your cluster. If you're running on one cluster versus another cluster on your personal laptop, on Amazon Web Services because they donated some time to you and so on, your setup should not depend on that. You should not be able to have to spend time setting your software up there. So Docker is a self-contained container. You launch a Docker container for running Spectre using just this. So you can download Docker, install it on your laptop, then run a single command here, and this will show you some options, and you can start a container, and then in that container environment you can start typing commands to run Spectre simulations and visualize output and so on. It's just as simple as that. Okay, you can of course install all the dependencies and everything by hand if you're into that kind of thing, but that's usually reserved for people who really enjoy that pain and so on. Okay. So there are some interesting tutorials here. this list is far from complete, and because this is an open source code, feel free to explore the code, and if you want more tutorials to be put on here, feel free to ask for tutorials to be put on here. How will you ask for that? So this is the GitHub page for the actual code, right? Just like any GitHub repository, this is completely in the same structure. Now, if you want to ask for this thing, you can create an issue here. Clearly, we have a 514 issues, so it might take a bit of time to get those addressed, but in principle, yes, you can ask for that. Now, let's look at the code just a little bit. I'm not trying to scare you, I'm just trying to make you familiar with what the structure looks like, okay? So, this source folder is where all the code basically lives in, all the important code lives in. What you will be interested in as physicist will be in this directory. Evolution systems, right? Let me just click on it. So there's a lot of infrastructure code. You don't care about that. That is just happening behind the hood. What you care about is implementing your equations that you may want to solve with, for example, or just Einstein's equations. So these are the set of physics equations that are already implemented, available in Spectre, right? So for example, for solving BNS, neutron star physics, you solve GRMHD equations in some formulation. For solving only Einstein's equations, this contains that generalized harmonic is the formulation of Einstein's equation. We discussed that, remember? Then you can solve simpler things like simple scalar waves in static curved background. So you can play around with scalar waves in falling into a Schwarzschild black hole, or going around a Schwarzschild black hole or a curved black hole and so on. That's one of the easiest things to start with. Then another formulation of Einstein's equations called CCZ4 is also implemented. So if you're interested in some research projects, it could have to do with, for example, comparing how identical systems evolve in this formulation of Einstein's equation versus this flavor of Einstein's equations. Okay. Then Euler equation, scalar advection equation. I don't know what scalar tensor is. Scalar wave is just the flat version of curved scalar wave and so on. Okay. So yes. Now inside generalized harmonic, you have the actual, so constraint, everything is hopefully quite intuitive. Constraints implements the constraints of your generalized harmonic system. Equations implement the evolution equations, obviously. Then initialize will tell you how to initialize the system where you evolve it, and so on and so forth. Yes. Sorry, say that again. Something like rank to derive. I don't know what that is. Yes. Well, not directly, but in mathematics, I think there's this function to export things into a C language. This is fully C++. This is 100% pure C++ with some Python thrown in for fun. Right? So if you can export your mathematical equations to C++, you can just implement it. In fact, if you are curious, the best way to start, as always, is scalar waves. Right? Just look at the scalar wave system here and see how has it been implemented. And you will go a long way. I mean, you can just reproduce it, start changing piece by piece to change the scalar wave equation into whatever equation you want to evolve. And it should just work as long as you have sensible initial conditions. And so Spectre has a very active developer community. If you are stuck with something that you may consider trivial, don't hesitate to ask the community. Just write to the people, and people are more than happy to have more. We are all more than happy to have people run all kinds of physics simulations, not just numerical relativity. All kinds of simulations for your, for example, courses. So one easy way of learning Spectre would be, if you're taking a course in numerical methods, try to do the assignments in Spectre instead of, Python, right? Or making ChatGPT do it. Don't use ChatGPT to do your assignments. Okay, yes. So what problems can you solve? I told you that the documentation of, the tutorials are incomplete, but what is not incomplete is this code. Code never lies, right? So this directory test slash input files, this has actual configuration files for a various or a series of problems take and run with Spectre right now today, which you have to know anything beyond, run Spectre dash dash input file space the file name, and you can run with that. So for example, Burger's equation, this is curved scalar wave, would be my favorite example again, right? So you can evolve a plane wave in Minkowski spacetime using this configuration file. So this is a typical configuration file that is to be provided to the executable, right? So once you start the Docker environment, type make space the name of the executable, this long thing here. We like long names because they are clear and not ambiguous. We can read sentences, right? We don't have to have small names. Once you have compiled that executable, you just run it with this configuration file and you'll get the nice evolution output, which you can then use, we visualize with standard software like ParaView and so on. And then you can play around with things in this configuration file. For example, there are various parts of the configuration files which are similar for all problems. Okay, so for example, this section under evolution, this specifies the integration options. What is the initial time, what is the initial time step, what are the time steppers that we use, what order of accuracy they have, and so on and so forth. Then this will also be there in all configuration files. This sets your domain. This is very important to understand. So you are creating your domain entirely here. You're only specifying the full domain entirely here. My domain is a single rectangular cuboid, right, which has some lower bound, upper bound. The distribution of points is linear. No, distribution of, sorry, the subdomains is the initial refinement level, initial grid points, and number of grid points per element, right? The domain is time dependent. For simple problems, it's not time dependent. For binary black hole problems, the domain will be time dependent. So it will be a much longer bit of configuration. And then boundary conditions in each dimension. So here is just periodic. So you can solve, for example, scalar waves. What you will see is if you throw in scalar waves along the x-axis, it will go and come back. And it will keep repeating infinitely, right? If you evolve this in curved space-time, and if you put a black hole in the middle of your domain, you'll find your scalar waves all get absorbed into the black hole. Okay. Okay, and you can evolve, for example, single black holes also quite straightforwardly. Again, same directory, tests, input files, right? I go into generalized harmonic, I look at Kerr shield. So this will evolve a Kerr black hole in Kerr shield coordinates. You can set the properties of the black hole. So this is the same code block as before, which specifies integrator properties under the name evolution. Then, stuff for AMR, you don't really care about how changing that, just let it be at the default value. Initial data, here you set up a black hole with unit mass and 0 spins. Feel free to change the spins to anything here. Okay. And then the domain, in this case the domain is a sphere, right, because spheres are more natural for black hole kind of simulation geometry, right? So inner radius of the sphere, outer radius of the sphere, what do we do in the interior? So in the interior we excise with boundary conditions, dirichlet analytic boundary conditions. We basically at the boundary we keep all the fields stuck at their initial values. That's what this part means. Then refinement of your domain, how many grid points you need per domain, and so on and so forth. So all of these options are actually documented in the documentation page. Okay, so now evolution system. I'll just go on for 2 more minutes and then let you go. So evolution system, you're solving the generalized harmonic evolution system. You remember the damping constants we talked about to damp away constraint violations, there were three of them: gamma naught, gamma 1, gamma 2 for generalized harmonic. If you remember long ago, like these are exactly those, and we are specifying them here. So damping constant 0, 1 and 2, and we are specifying them as actually fields. So you'll see they're not single numbers, they're actually fields. They depend on the spatial coordinate. So we have a profile which is Gaussian plus constant, where the constant value is some value and the Gaussian width is also specifiable, and so on and so forth. So all the things that I have mentioned here and there are, in code. I may lie, but the code will not if it has to work, right? Okay. So filtering we didn't talk about, but that's sort of beyond 2 lectures. And yes, the most important part is uh, this part. Yes. How do you get anything out of these simulations? To get out of these simulations is we use a concept that we just call observers, because physicists, right? We call that observation. So triggers. At certain triggers, you observe information, right? So triggers at every time step, or at every 2 time steps, at every 3 time steps, at fixed number of time steps. If you do it at every time step, then it will depend on the integrator's mercy. If the integrator is stepping 0.1, 0.1, 0.1, then 1, 1, 1, 2, 2, 2, 2, your spacing in time will depend on that. But if you want a fixed spacing, you can specify that also. Then that's just the trigger. The event is observation. This part tells you how to actually observe any field or a combination of field or some norm or whatever. You can do integrals just in this configuration file and observe that integral and so on. Okay. So for example, here is an observer which observes the norms of some variable. So what do we want to observe here? For example, we want to observe the numerical errors, say. So this whole bit is about writing down the errors in spacetime metric pi and phi tensors. The kind of norm is specified here and so on. Okay. Then you may want to write down the constraints that we have. So in this presentation, I showed you this, this figure right here. And in code now I showed you how exactly that figure came about, right? By yes, through the pointwise norm of gauge constraints and so on. Okay, so I think that's it. I have exceeded my time by quite a bit, so I should stop here. I'll put up this slide and wait for questions.